Thank you all for joining us today for our Energy Institute event. I'd like to say a great warm thank you to Professor Augustin Valera Medina for joining us. I'm sure we'll be very interested in what he's going to say. I'm not going to try and preempt that at all, because obviously he knows a lot more about it than I do, or we would be inviting him. But what I would like you just to be aware of, as well as the actual presentation, there's going to be opportunity for Q&A at the end. And I'm going to preempt a bit of the closing remarks, jump to them, just in case I forget. So just a reminder that here at the South West and South Wales branch of the Energy Institute, we have lots of opportunities for you to join us and be in the branch at various different levels, starting from student all the way through to fully chartered. When I joined, we were only just starting the petrol industry. And it was actually a bit weird being one of the renewables people, but there's been a huge transformation in the Energy Institute over the period, and now they really are forging forward to the net zero world. And our next event will be back in this building on the 12th of June, when we'll be having another speaker. We'll be having Manu Pirasoglu, who is a researcher here at the Welsh School of Architecture, and he'll be talking about his research. And we'll get an opportunity, we're going to risk doing the hybrid for that one. We'll see how well that works, but certainly if you join us physically, there will be a presentation. It'll also be our annual general meeting, where we have an opportunity to vote in our future committee leaders. And any more information on that, feel free to contact myself or Emily. Emily's done a lot of the setting up of this event and joined us all the way from Cornwall. So Emily, thank you for making it here and doing all the background stuff. And I'm going to pass on now. She should be fine just with the cursors.
Perfect, yes, absolutely. Yes.
So, thank you very much.
Let's see and hope the quality improves as I go along. Otherwise, I think we'll have to use then my laptop. But anyway, let's see. Okay, yes, it's going to improve. Okay, yeah, no, thank you very much for the invitation, Vicky, Emily, everyone I know about, Rich, obviously, and all the team. Again, I've known for a long time. So my presentation is going to be on ammonia as a net zero fuel. Probably you've seen some of these slides already, probably not. And the idea is to then expand and disseminate a little bit of the work that we've been doing on ammonia and how this could be, as mentioned by Vicky, one of those net zero fuels that potentially can feed the future. So as part of the presentation, I'll have an introduction, some of the challenges that we're facing when we're talking about the use of this chemical, developments that we have done as well in some areas of interest that have practical applications for the energy sector, collaborations that we got, just a quick slide on that, and then final conclusions that we have found across all this research. So the introduction starts with this, we know it all, is renewable energy that we can then capture from different sources. So we got the wind that is well established, solar, and there's a lot of talks now about marine with all the different components and systems that can allow us to then recover all that massive amount of energy. What is always the problem is the intermittency that these sources face. So we know that one day that is not good enough for blowing the wind, and then can be enough to then live around 2 million people without any power. So this is something that happened probably 6-7 years ago. You might remember that happened in the Midlands, where the news documented that around 40%, 50% of the UK or that region were actually running on wind power. And something happened in the North Sea, the wind farms, and then things stopped happening, eventually just reducing the power input into the grid. So that was a big problem. Australia suffered a similar thing a few years ago. So this always shows that we have that intermittency factor that needs to be surpassed via some other ways of storing energy. One could be batteries. We have talked about compressed gas. We have talked about many different sources. And one obviously is chemicals, chemical energy that we have learned to use for centuries, millennia, and that we're still using today. It's probably going to then feed the future as we go along. So these are some of these different technologies that have been on the playground to then deliver some of that storage we're talking about. Batteries, obviously, capacitors, hydro and pumps, mechanical storage like compressed air, and some other different methods that now are in the scope of research and developers for commercial applications. But one that always comes is chemicals. So again, we have learned how to use for over centuries. Methane, oil, coal, etc., all those kind of chemicals that we know how to employ, and now these days talking about then decarbonizing, bringing down the CO2 via net zero or low carbon vectors. And among those we have hydrogen and ammonia. That could be one of those ways as well to then deliver some of this hydrogen that is required worldwide. This is a really nice and interesting map that I love to show in absolutely every presentation I deliver, because it's been written by the Hydrogen Council, and this goes back to probably 2.5, 3 years ago when they released it with all these different analyses looking into the different ways to distribute hydrogen. You can see here on the bottom that we have all these localized resources where natural gas is just located in very particular areas across the globe. Whereas in the case of renewable energies, photovoltaics, wind, we got absolutely every part of the planet that is essentially capable of producing some kind of renewable energy. But the important part of the story comes when we do the analysis on the economics and the delivery of that hydrogen. So for them, the important aspect was how we're going to then deliver or move around the hydrogen for, say, a location that is producing a lot of that renewable energy, say, for example, Chile, and that being distributed to the US that is going to consume it a lot. Similar scenario would be Saudi Arabia or the Middle East going to the European Union, or, for example, Australia or New Zealand going to Japan. So as part of that, they normalized the whole thing, did it US per kilogram hydrogen, and came up with 3 solutions to then distribute that hydrogen. One ammonia, the other one liquid hydrogen, the other one liquid organic hydrogen carriers. And as you can see from the numbers, from the clean production that would happen in that heavy energy located zone to the final destination, coast at port, the numbers are similar between them. So 3.5, 4.4, 3.2, 3.8, 3.5, 4. Okay? But the interesting bit is that if you look into the part of ammonia, what happens is that the cracking concept is taking around 1/3 of the total costs of the distribution of hydrogen. Meaning that if we can then reduce or completely remove the cracking of the hydrogen, this becomes the best solution, again, by a massive portion in the economics of distributing that hydrogen. So that's where all this research comes from, because ammonia can be used either fully as comes as ammonia, or again partially cracked into some components of hydrogen, and you'll show you some of the stuff that we've been doing along those lines as a fuel. And it's interesting because we can then use it in that way to distribute for long distances, but also can be used to recover stranded energy, waste streams. One of the things that is interesting as well is that because we have a molecule that we know how to use and we have used over 150 years, we can reduce the cost of actually storing and moving around that hydrogen. It's very simple. We have cylinders that contain liquid ammonia, slightly pressurized, and they can stand there for months, if not years, without major problem. Whereas we have the case of hydrogen, as we start storing this for long periods of time, then it becomes expensive, high pressure or cryogenic, which means again sometimes 30, if not more times the cost that ammonia would cost us. Can be produced in islands or isolated locations. It's obviously a fertilizer that we have used for that period of time, but now we're looking into it as a fuel and has more hydrogen than hydrogen itself. And I was like, what is going on? Well, it is, because we have in ammonia 3 atoms of hydrogen compared to then 2 atoms in the hydrogen molecule. So actually has around 27% more hydrogen than hydrogen itself. And then finally, we have a very well-developed, mature infrastructure that is moving around 200 billion euros per year just on ammonia. And that is going to then expand 5 times just on the fertilizers. So it's one of those cases that, again, just shows that there's potential. Now, one of the questions that I always get is, where are we going to get that ammonia from? We're talking about not only for fertilizing, but as fueling vector. Well, the whole story goes, as right now, we're producing around 90% of that ammonia via conventional methods, just methane reforming, loss of CO2. Actually, it accounts around 3% of the CO2 globally. Now, what companies producing ammonia are trying to do is move away from that and then get into what is called Generation 2 ammonia production. Generation ammonia 2 is using electrolyzers that are fed by solar or wind systems, and again produce the electricity required to produce the hydrogen that then eventually gets mixed with the nitrogen that is sequestrated from the atmosphere to then get them into these big reactors, Haber-Bosch systems. And that produces the ammonia that we can use for generation 2. Problem is that they're still expensive. Electrolyzers are just too massive. And again, it's just like one of the big tolls. So ammonia produced this way is still very expensive, 3 times more expensive than this way. But then the third generation, that is the one that is the one that is promising, is getting rid of the Haber-Bosch process. This reactor that we have in between is going to be removed, and using fuel cells and materials that will combine at surface level these hydrogen and nitrogen will then produce ammonia directly. So the process is that instead of having an electrolyzer that is going to produce that hydrogen and is the expensive part of producing the ammonia, then it will be only water and nitrogen that combined together will produce straight away ammonia. Now, interestingly, is that compared to the efficiencies that we got now in generation 2 electrolyzers that are in between 56 to 60%, these now are producing efficiencies of 42. So it's not that far away to actually start getting into those numbers that will start producing ammonia for that. And if this happens, what that means is that anyone that has access to some renewable energy that we've seen is all around the world, water and nitrogen, will be able to produce ammonia. So that means that anyone in the globe will be able to produce their own energy. Again, and store it as they want. Use it as a fertilizer, use it as fuel, use it as a working fluid for thermodynamic purposes, anything. So that could then change the whole agenda. Now, the important thing is, again, to get to that stage. But in between, we are trying to develop technologies that will help us, once that happens, to then use the ammonia efficiently. So this is more or less the map that we have, and it shows that we have renewables or methane reforming, producing that hydrogen, or connecting to the grid directly. And if we want to store it, can produce still some hydrogen, because hydrogen will still be needed. Is the case that ammonia is going to be a support to that hydrogen agenda. It's not going to be the final bullet. It will have some niche applications, and I'll mention about those. And then finally, if we want to store it for a long period of time, ship it, or distribute it for long distance, we go for ammonia. So it can then support all these different aspects: transport, heating, cooling processes, propulsion, stationary power, etc. Now, there are many things that still we don't know, and some of them have to do with fundamentals, so reaction and combustion. Those kind of things are what we are studying here in engineering, because the reaction of nitrogen is very complex. So once that we start burning it, then we know some cases and some conditions that we can then bring down NOx emissions. But still, the reaction mechanism modeling that exists at the moment hasn't cracked what is going on at different pressures, different conditions, different flow rates, etc. That still is unresolved. And we're talking about an area that has been around for probably 60 years. So fascinating area. Public perception is one of those topics that is probably going to be the most important in the development of these technologies, because communities, people perceive, and it's again the way that actually ammonia works as a toxic chemical and also smelling, a nuisance. So one of the things that I'll mention about is public perception in different areas. So for example, countryside, they are used to some ammonia smell. and 1-2 parts per million from the manure coming from the cattle, poultry, etc. Whereas in cities, they say, no way, this is not going anywhere close to me. Regulations, we don't have any regulations. Again, when it comes to fueling, economics, we need to then make it affordable. We need to make them reliable. We need to then have ammonia being produced at the cost that we're producing it right now. Otherwise, this won't work. And then finally, the environmental aspect that will come with the dumping of all that nitrogen into the atmosphere that hasn't produced. So we got ammonia that is being produced in Morocco and then that is consumed in the UK. How is that going to impact the nitrogen cycle? We don't know. So along those lines, we have that ammonia presents a really nice energy density, higher than the one that we got with hydrogen, even liquid or pressurized. Lithium batteries as well is much higher. It's not as high as the carbon-based fuels, but in some cases, for example, as methanol, is close enough. And when it comes to the long distribution cases, shipping, rail or lorries, we have as well the case that ammonia is the most cost effective. So again, there are some areas where ammonia will play its role. So it's very likely that we'll see it in shipping. The shipping industry is nowadays developing internal combustion engines, large size, again, 2-stroke, that are putting this together. The latest news was just a week ago that MAN has finally finished with the support from several South Korean, Japanese manufacturers, the first unit that will be put on the sea in the next month. And with that, they want to replace many others as part of their commitment to reduction of emissions in the various Asian countries. Rail as well, heavy duty, large, long distances will be another area that has a lot of potential. Because again, the requirement of ammonia that you need to then drive or move a train will be lower than the one that you will need from liquid hydrogen. Because again, the amount of liquid hydrogen that you would need to then do that same trip, and then finally lorries that would require heavy loads in combustion base. So when it comes to the combustion is when we have the heavy duty that just plays better than the fuel cells. These are some analyses done on the efficiencies. You have, again, the cases of the hydrogen, the ammonia, the methane, and the methanol. And all those cases show from the renewable energy production to the final consumption or production of electricity that in the cases of the ammonia, the methane, and the methanol, the efficiencies are almost the same. Now, in the case of hydrogen, where do we have the highest losses? In the cryogenic storage. This is where all the problems occur. In the case of the ammonia, where we have the losses, are in the Haber-Bosch and the electrolysis, but as you can see, it's around the 70s, the 60s, and then the storage, because it's again very efficient, it's around 99%. We have again, and systems that we've been operating for years, drums that, for example, during the COVID period, we just had there standing because nobody could access them. After a year and a half, 2 years, we would come back and they would just operate as if it had passed just a few weeks without using them. A little bit of wearing from the cylinders, but nothing major, nothing that you would say is going to stop us operating. And the same way, we have the other cases, and then as carbon-free fuel comes, then this is an option that is feasible. This is another study, really interesting, done by the University of Minnesota, and what they were trying to demonstrate was the feasibility of either a hydrogen, ammonia, or a combination of both economies on all these different cities. So based on the location, they would then have case, for example, Miami to be more hydrogen based. So this is levelized cost of electricity. And if it was something that was, for example, Miami, would be that is more hydrogen because it has offshore facility. Hydrogen would be easier to transport or move around. Whereas in the cases, for example, of Houston being far away, will be probably the ammonia that is closer to the ammonia line. But when they combine both of them, the hydrogen and the ammonia, the levelized cost of electricity was the lowest. And all had to do with having smaller production facilities for the hydrogen with the smaller storage facilities for the ammonia, CAPEX. And then finally, showing that the combination between both of them could complement each other, and thinking about the hydrogen is something can be used straight away, can be employed for fuel cells, can be employed for civil transport or in use in cities, whereas if we're thinking about ammonia, could be the seasonal storage, could be long distance transportation, could be the use for heavy duty in farming locations. So it's got a lot of capabilities, and that's the reason because the International Energy Agency in 2018 finally gave it a ranking of being a fuel. Before then, if you look into 2017, there's nothing about ammonia. It's just like an explosive or a chemical, and it's until 2018 that actually this diagram appears with power industry and shipping. And with that, many agencies across the world, especially in Japan, China, and South Korea these years, have been taking over the use of ammonia. Singapore is another one that is a very strong one, and is now looking into decarbonizing the port using a combination of both hydrogen and ammonia. So these are some of the details about the places where we can use, and we know we can use ammonia. We have the fuel cell realm, where we have efficiencies between 40 to 55, and in these cases we have challenges that go from cost and sensitive exposure to ammonia traces, to then finally what is now the development of some of these systems. For example, solid oxides, we know that they're going to be probably the future, but they are in development stage. Whereas in the cases of internal combustion engines, gas turbine cycles, furnaces and boilers, we got already cases that are industrial. So internal combustion engines, we have the marine sector. In the cases of gas turbines, we have as well Japan leading some of these in some facilities that they're demonstrating as we speak, 2 megawatts, 3 megawatts power. And this one is the one that is the most interesting at the moment, furnaces and boilers, because furnaces now are showing efficiencies between 85-90%, and we're talking about gigawatts of power. So the latest is developments that are conducted by a company called IHI. They are in collaboration with some energy and electricity producers in Japan that are now changing up to 50% coal for ammonia. So it's co-firing ammonia coal, and they're now using 50% of that using ammonia. The amount of ammonia that they're employing is in the range of 500,000 tons per year just to do so. Now, as part of the challenges, we got 4 that we have identified. First one is we need to then have carbon-free synthesis, cost reduction and efficiency, as you've seen. Again, as I mentioned, the problem is that we still have this generation 2 ammonia too expensive, and the generation 3 hasn't arrived yet. If it arrives, again, we never know. Power generation at utility scale, it needs to be stable and with low emissions. As I mentioned, we have NOx emissions that we produce as part of the combustion of ammonia. We are now targeting that. That's where the name of the game is at the moment. Public acceptance with safe regulations, because we don't have regulations yet, and the public acceptance as well just considers the case of ammonia being too toxic or too dangerous, and then finally the economics that need to be profitable. These are the 4 challenges that we need to surpass before we get ammonia running. So getting into some of the technicalities and some of the combustion, we have done a lot of work, and this is something that we got from some literature, and that's really interesting, that shows how the use of ammonia and hydrogen changes. And these are the kind of things that we're facing when we are doing the research. So on this side, we have the amount of hydrogen that we can use, and on this one, we have the pressures of operating these systems. As we increase the pressure and increase the amount of hydrogen in these ammonia hydrogen blends, what will happen is that they will become more unstable. So cases where we have just barely any hydrogen, 20% up to 40%, are actually stable. They allow us to play well. But once that we have passed that point, the hydrogen takes over, and then what occurs is that it becomes extremely unstable. So those are the kind of things that we are now facing. What would be the best blend to actually use in these systems that will allow us for the ammonia to then be born, but then combine it somehow with hydrogen that we can obtain from the same ammonia to to then stabilize the flame. And that is some of that research that we've been doing. These are the kind of flames that you will see between one and the other, and it shows how different they are. This is a case where we have natural gas, again, a nice blue flame like the ones that we got in stoves, and this one, an orange flame that is purely ammonia. So it's just the changes in radical formation in chemistry that are happening with, again, combinations of the stability of the flame, one that is hydrogen that is very fast moving into our system, flashing back, whereas the other one just taking its time much longer to then do so. But at the same time, it's been more prone to then be blown off. So these are some of the research that is been going on that has to do with liquid injection. And most of the developments at the moment have been relying on vapor ammonia because it's simple. We can then use waste heat and then produce the vapor and in that way improve the combustion. But one of the ideas and best ways to use, for example, internal combustion engines, the ammonia, is to spray it into the cylinder, similar to having diesel or gasoline or anything that is liquid. So that way we can then improve the process overall. And that is an area that is really interesting because ammonia, as it gets hot, it will start then flashing and then vaporizing and then producing in different patterns that are difficult to determine. Similarly, once that we start pressurizing it, then things change and these curves, penetration and how we get the fuel in just start changing. So again, lots of things to be learned. This is an area that probably has just 2.5 years since it started showing up in the literature, but it's still growing with modeling and implementations. This is a layout done by the AIST Institute, one of the research institutes in Japan that has been leading this ammonia agenda. And you can see that eventually they had some evaporator that would then feed combustors, and now they're looking into the use of liquid ammonia to then directly feed into these systems. Now, with that comes a lot of challenges, and again, things that we're trying to learn on how we will produce onboard ammonia. It will produce NOx emissions. That is the main emission that is produced when we are burning the ammonia molecule because it's got nitrogen in it, and then finally reduce that in a way that is not polluting. If we get to a point of producing a lot of N2O, then N2O is 300 times worse than CO2 in terms of climate change. So the global warming potential is 300 times larger, and that means that with just some parts per million of nitrogen N2O would be enough to then throw to the window the reduction of CO2. So that's the reason, because this is a major challenge, especially when it comes to these liquid injection systems. Another interesting area that again just like blows up imagination and then the way that things are going is the use of plasmas. Plasmas that have been used for ignition or for other purposes in physics now as well are on the target to use ammonia in an efficient way. So what is the process? We have a very intensive energy field that is produced by these plasmas that eventually will start producing radicals that can then start interacting before they get oxidized. So that means that we can potentially bring down the emissions as we got them and also improve the flame as it is. So laws of physics. Now, for example, I read for the first time one that had to do with magnetic fields. So how magnetic fields are trying to then change the flame, ammonia flame, and then by making it more concave, increase its stability and reduce emissions. So things like that again are just people are trying to use with more creativity, combining different fields. Some of the work that we have done in internal combustion engines has to do with a unit that we got in STFC in next to Oxford. And this was a very interesting project because what we had was a wind turbine that is operating around here, an air separation unit that is in this container developed by Siemens. Then we have this other system that was an ammonia producing device that was designed by Oxford, and a storage facility, and then finally a container with an engine that we developed. So with that, we demonstrated the whole process of capturing that wind energy, passing it through all the process, and then finally generating energy back into the grid. So that's something that is how we started with internal combustion engines. And with that, we have then looked into some of the work that is going on. So with that, in the cases of transportation in Korea, they have taken a lot of work in the same way that Japan, and now things are happening in Canada with fuel cells. In the shipping world is more concise. There are more things going on at larger scale. We're talking about 2-stroke large engines, and they are now promised to then be in commercial applications by 2025. So we're not that far away. We're just a year away to then getting to that point. And then finally, for farming, because again, being fertilizer could be one of those cases of receiving the ammonia, and then once that we got it, then depending on the season, use it as a fertilizer or as a fuel. That's one of the concepts that, for example, in the US they are looking at, because they have a pipeline that feeds directly into gas stations. So these gas stations, they receive the ammonia directly. They pump farmers into their nursing tanks the ammonia, and then once they got it, they use it to plug the field, which is something that's really interesting. But in the same way, they could use it and then plug into the truck, and then that way feed it to then use it and move it. So it can be used again without any problem alternating between a fuel or a fertilizer. As part of this program, some of the studies that we have done have to do with using the ammonia for again shipping and long distance or large distribution, and then with that a concept that is a city gate terminal, similar to what we got with heavy voltage electrics, would have something that allows for the ammonia to be received, and then from that point either crack it and then produce hydrogen for the cities, or use it as ammonia in rural locations, when, as I mentioned, can be used for heavy-duty trucks, can be used for stationary backup power, heat cooling, or even stationary large power generation. Because again, most of these systems, large power generation, they do have ammonia facilities for inoxing. So they know already how to handle the ammonia. So it's not an unknown for them, it's something that is a given. So this, if they can then replace it, would be a way forward to decarbonize relatively easy. These are some of the cases when it comes to internal combustion engines of all the complexities that we got to then sort out when we start mixing with the different vectors. So we have natural gas, syngases, gasoline, DME, diesel, etc. And as you can see from all this table, we have cases where the ammonia, onboard ammonia, the NOxes increase or decrease. We have hydrogen that sometimes shows up, hydrocarbons as well in the same case scenario. So this just shows what is the complex scenario. And many companies, many institutions working together with industrial ventures are looking into very specific cases to then try and decarbonize some of these using ammonia. Again, the challenge is that they are so variant, they are so different, that once that the ammonia starts mixing with some other molecule, it starts producing very different patterns. So that's where the research is. And again, they give us a lot of opportunities to then do a lot of work in the institutions. Fluidized beds, the same way that we got in for biomass, can be as well employed for ammonia. And these are works done by South Korea, where they're looking into the use of these type of systems to then better produce energy and use some of the waste that they're producing already in locations, again, like farms where they have some ammonia available. Boilers and furnaces, as I mentioned, is a very interesting one, because what we got is cases that are already on the industrial scale. We have systems that have been developed for refineries or oil locations where they do produce a lot of ammonia as well. We have the case of steelworks, where they are now trying in Japan the use of this ammonia for furnaces. So as you can see, the difference between the natural gas and the ammonia flame, the one that is the bluish and the one that is the orange, and one that is a very successful case that Chinese are bragging about that's really interesting is in Guangzhou. And this is for the tiles industry. So now they have a line that is 200 meters long, replaced entirely with ammonia burners, that is producing tiles that are against zero carbon and apparently with better properties than the ones that they have with natural gas. Interestingly is that in this particular project, the whole idea of having it in this system was that at that location, there are 300 companies producing tiles for the global market. And they're pushing to then remove the natural gas using ammonia because they have demonstrated already that it's feasible and they can then do it. For us, an interesting area is the replacement of LPG because we have a lot of communities across the UK and Europe that are right now using LPG. They don't have any connection to the natural gas grid. They have poorly connection to the electrical grid. So if we think about electrification, it's going to be too expensive. Or if we think about having this hydrogen promised line, it's never going to happen, or at least not in the next 10 years. So that's the reason because until now, they still use and operate using LPG. And this goes as well to some farms that do processes, distilleries, poultries, etc., just for heating applications. So doing some analysis, techno-economics, we found out that bringing the ammonia would be the most economic, feasible solution compared to even the liquid hydrogen. And I always get why, if you are producing the ammonia from the hydrogen, is more expensive. Well, the main reason is that you will require more nursing tanks to deliver the same amount of energy being on hydrogen than the one that you would require with the ammonia. So again, for these particular conditions, it will be better to then bring the ammonia because it will be more energy dense. Similarly, some of the components that they use already in LPG can be used straight away using the ammonia. And the reason is that most of them are made out of stainless steel. The evaporators, stainless steel. The temperatures of storage is for LPG minus 42 centigrades, and the one for ammonia is minus 33, so very close. And properties very, very suitable for most of the components. So that's the reason, because right now we are developing a 1.52 megawatts power unit boiler with a company called Flowgas. On similar thoughts, we were exploring with Tata Steel the use of some of the ammonia that they produce in Port Talbot. It's around a ton that they produce per hour, so it's like a massive thing when they are operating producing coal gas, and that could produce over 5 megawatts of additional power just using this concept. Again, things that can be evaluated and explored further in other projects. This is the kind of development that IHI, this company I was talking about, has been doing with this co-firing pulverized coal with ammonia, and lots of different things, engineering aspects, beautiful analysis on different nozzles, and depending on the nozzle, they would have more or less NOx emissions, again, things that have to do with the flame itself, and the fundamentals of having the combustion of these two different chemicals. So you have particles, they will start producing energy, but at the same time will produce radiation, consume radiation, etc., that will then change the patterns of the final system. Right now, the dream is to then get to 100% ammonia in some of these systems, but the target up to 2025 is 50% replacement. Again, they have managed to do that with around 500,000 tons of ammonia that are being shipped into a place in Japan, close to Tokyo, that is now powering using ammonia. Similarly, IHI is selling these burners already to Malaysia, to India, to Singapore, and now South Koreans and Chinese are replicating. So in this area, coal production is probably the way to go, because temperatures are, the range of what ammonia will be produced, and because they're not that high, then what happens is that they actually denox some of the system. So one of the things they found is that once that they burn at 50% coal, 50% ammonia, NOx emissions are lower than burning pure coal. And at the same time, because of the radiation that is being produced, they increase the efficiency of the system. So right now, 50% ammonia, 50% coal is the best way operating these furnaces. And the main problem is right now the cost of the ammonia that is still too expensive to be used. Some of the areas on gas turbines, these are some of the tests that we have done in our facilities, and they show different trends. And depending on the system that you got, you will have some reduced oxygen in some of them, then increased oxygen, and that will bring down those NOx emissions, nasty pollutant that we got in the burning of ammonia. So that has been very revealing, because as we have progressed through the research, similar way and independently, Japanese universities South Korean universities, they're finding similar trends, which again give us confidence on what we have been doing. That has given us potential to then design, patent this burner, and the idea is to combine different aspects of the recombination of these radicals, these species that happen across the flame, and then bring down NOx emissions to almost 0 parts per million. Now we have some onboard ammonia, but that's what we are working on now. So we can then recombine them with different parts of the flame and then finally produce as low NOx emissions as possible in this type of systems. So with that, another area of research that we have been doing and is really interesting is the one on materials. And this is something companies haven't realized, not all of them, that will happen. And the problem that we got with ammonia is not only those NOx emissions, but also how they will impact on the materials that we're using. These are two examples of having natural gas and ammonia hydrogen on an Inconel material. Again, the kind of high temperature materials that we see in power or process concepts. And you can see that this has been nitrated, again, all black, and again, it's just been degraded, whereas this one hasn't suffered much. And another problem has been all this hydrogen embrittlement that is just showing up in these at different layers. So that is something that we don't understand. Nobody understands it because, again, it's an area that just probably started a year and a half ago, again, in the literature. Nothing much, apart from some tests in the 60s that didn't give much information. This is an active area that has a lot of potential. A larger scale, we've been working, similar to other institutions, with companies like EDP to produce power in a place like Portugal, with concepts like this one, where you can operate a gas turbine, and then the gas turbine, once that is on off-peak power, will keep operating at that same power level to then produce ammonia. So get enough power to the electrolyzer, then produce the hydrogen, then get the ammonia synthesis. So once that we are back into peak consumption, we can then release that ammonia or crack it, producing hydrogen, nitrogen, and then feed into the unit. With that, then we do calculations and analysis on the size, the storage capacity, and all that for this power unit. That's something that is ongoing, and the interesting results that we got now from that research. So these are the kind of turbine players that we know about, with Japan, with us, with Norway, Saudi Arabia as well, Italians already working as well in some of these analyses, universities in Belgium, the US, and also China doing their own contributions. As you can imagine, US is like picking up very fast because of the investment that they got. So they're moving into what is our research 2 phase, where they are now demonstrating combustors at a medium to large scale, and then the phase 3 where they are implementing everything into these units. Propulsion is another interesting area, and this one goes back to the 60s, 70s, where that unit, the X-15 rocket, managed to get up to Mach 7. The time, nothing was faster than that, and it was until the shuttle was launched that actually this one lost its record. But it was based on ammonia and liquid oxygen. And then with that came a lot of developments, especially for satellites, where they use it still for propulsion systems, because again, very easy to store, and then allows for the correction of an alignment of satellites. One interesting thing is people talking about this as a potential fuel for aerospace applications. And again, we go back to the case of liquid hydrogen. So in the case of having an airplane with a capacity of 70.5 cubic meters tank, we would be able to then fly at a long distance 100%. That's our norm. Then if we wanted to then use liquid biomass, that would be reduced to 68%. If we wanted to use liquid ammonia, then that would go down to 39%. Again, this based on the amount of energy that we would get from that system. And then finally, if it was liquid hydrogen, it would be 29%. So again, it's just showing how feasible and then more dense ammonia could be, and the option. And we're talking already that are developments going on in terms of liquid hydrogen propulsion. So one of the things that comes back and that is haunting us in terms of the use of liquid ammonia for aerospace is the public perception. public perception on how ammonia would be distributed, what would happen if there's an accident, and what if, for example, some of this ammonia is released in the middle of the ocean. Now, those kind of questions are the ones that we need to surpass again with public perception and then working with these companies. But as you can see from all these thermodynamic analysis done by Germany, they managed to then get some of these sorted out, at least just recognize quantitatively what will be their impact. And in terms of, for example, comparison with jet fuel and some other vectors, methanol, methane, hydrogen, ammonia or ammonia hydrogen, the ammonia hydrogen came back very nice positively in most of these aspects, again with a 5 with CO2 emissions, 0 electrosynthesis, etc. The ones that came out as the poorest were obviously the toxicity that again just involves what is going on with ammonia. But as I said, this is a chemical that we have already in Heathrow, and 10 megawatts refrigeration unit is operating on it. Now, the difference is that it's not as a fuel, so that changes everything, and the regulations will have to then change. So with that, some companies on the unmanned vehicles area, or even again thinking about propulsion, companies like reaction engines that have been looking into different options, are now considering the use of ammonia. Now, not directly, because again, we don't know how that is going to then play its part when we're talking about high altitude combustion, but as a method to distribute the hydrogen. That could be the beginning, but eventually it could be one of those ways that without having any cleaning of the gases coming out of that process, we can then do it directly. Then we go into the public perception, again, that aspect that is haunting us and that is not allowing us to then do more. And again, it has its own valid reasons, but at the same time, I'm going to show you some of the aspects that come with the use of ammonia. Recently, the Environmental Defense Fund published this study where they were analyzing the oil spills impacts compared to the ammonia impacts. And they characterize cases for bacteria, plankton, macrophytes, invertebrates, reptiles, fish, birds, and mammals. And as you can see from all the points, they're almost the same. The ones that change are essentially invertebrates. So things like penguins will get more exposure or more impact if they were in contact with oil spills. Again, we've seen that in the media when they just come out from all these nasty oil spills, BP, for example, what happened a few years ago, and then they've been all covered on this nasty layer of oil. Whereas in the case of ammonia, it wouldn't be that impactful because it will dilute. Whereas in the case of the fish, because the ammonia will change the pH, that will have a direct impact and then change, potentially killing everything that is in the surround. Similarly, birds would be one of those cases. Again, that could be again as the birds. Did I say invertebrates were penguin? Sorry, it was the other way wrong. Yes, invertebrates again, no vertebrates. And birds again, the penguins will be the ones that would get again the impact, and the invertebrates again, starfish or etc. Sea animals will get that nasty layer of oil cover on. And then another study done a few years ago, around 15 years ago, was on what would happen if we had a petrol station being fueled with either LPG, gasoline, or ammonia. And the study showed that if we had gasoline at the close proximity to the pump, it will have more impact than ammonia, because ammonia will take its very long time to start evaporating and actually producing a nasty cloud. If it was a longer distance, then eventually what would happen is that ammonia will reach further away, and then that compared to LPG would be worse. And we're talking about LPG already being in communities, in farms, in heating processes. So this is something, again, that needs to be looked at. And the final one is a study that analyzed the amount of deaths from the 1970s to the 2020s between all these different cases in highways, rails, and water when ammonia was released. The ones that you see here in brackets are the ones that are again reports that have been part of our official documents. So all this is recorded, and then we see the total fatalities that happen over that period of time. So if we see here, we have around 36, 40 deaths in a period of almost 50 years. So that's the kind of toll that we get from the fatalities of the second most distributed chemical in the world. So again, the amount of deaths is so low because the regulations are well established. Now this goes in the US. So in Europe, it's a similar story. We got around 50 over a period of 50 years, whereas in other economies like India, in Malaysia, South Asian countries, Africa, etc., that number is much, much higher because nursing tanks have accidents, they release all the ammonia and then kill even communities at the extent of 150, 200 people in a go. So it is regulations, but we need to then use ammonia as a fuel that can decarbonize. These are some other studies that we are finishing on premature deaths when it comes to the use of engines that could operate on either diesel or ammonia. And here you can see that the case of ammonia, when it has after treatment of gases, just brings down those numbers to extremely low, much lower than the ones that you would expect from diesel engines. So again, it's one of those cases that shows that ammonia under the right conditions and the right system could be even better than the ones that we're already using. It's again that public perception that is still stopping it to then get. This is a final study, and I think it's the last slide that I got that shows what is the perception from different economies to ammonia. And it shows that in the case, for example, UK and Mexico, there are a lot of differences, but the main ones are related to these two aspects. The one that is poison and the smelly nuisance that ammonia can produce. You can imagine in the case of the UK, regulations are strict, and the main problem is actually being a nuisance that is going to be smelly. Whereas in the case of Mexico, it's going to kill us. And again, it goes back to then having regulations that are up to the task to then reduce any exposure or any toxicity that can actually kill an entire community or anyone that is operating with that. So once that this was analyzed, once that some infographics were shown to the people working on these workshops, it was clear that they changed their perspective, they understood much better, and then they realized ammonia could have a lot of potential to then decarbonize, as long as it's well regulated. But this is something that needs to be done. So this, just to wrap it up, some collaborations that we got with many industrial partners, universities, etc. We are working on, again, different areas of interest. So anyone interested in working on this, you're very welcome. It's like always trying to then bring new ideas. And these are some of the stuff, nice as Rich saying, just for the show. So we have a symposium going on in Shanghai. We have a book and we have a journal that is related to this sector. And that's it. So ammonia can be used to decarbonize all these different aspects in the economy. Anything that has to do with thermal applications, cooling, heat power, and propulsion has been used, will be used, and will be part of it. Important thing is to then bring down those emissions, make it more stable, and obviously then comply to regulations that are strict enough that allow us to do so safely. There are still many points in combustion, for example, in our research area, that need to be understood. And as we are talking, there are loads of institutions and now companies interested in making this happen, and the topic has gained a lot of acceptance. We still need a lot of research and development to be done. Now the name of the game is demonstrators. So we need more demonstrators to then show at utility scale this is possible and that can be used safely. And then finally, in thinking that if you can then surpass all these barriers, it's potentially that ammonia will be with us as a fuel in the next following years. Probably everything goes as planned, starting anytime soon, the earliest of this day, the end of this day. And that's it. So is there any question?
I'm really interested in this presentation. And I'm doing energy storage for the brain. So when you talk about ammonia as a storage backup, I wonder, do you have any details to share about what the plans are going to be? Because I think when we talk about energy storage using ammonia, I don't see a lot of research going on. I think simply because we're looking at how competitive it can be ammonia and the intermittent response time. Because when we backup rate, we think about how quickly it can be, what the function is. So I'm just wondering what is the function of ammonia and what the duration we're talking about.
So when it comes to the storage, again, we can store it for as long as we want with very low pressures. 8 bars, you got it converted already on the atmospheric temperature into a liquid. They can stand like that for months, if not years. And I'm just giving you one example, a simple one. We have this 500 kilograms container that we didn't operate for that period of time. The only thing that we got at the end was some rust from the cylinder that was produced over the year and a half that we didn't operate. That's again, we didn't have to take care of it, and as long as no person would go into our facilities, it would be enough. Will be fine. Now, when it comes to the production, or probably again thinking about how we're going to optimize it, it's being a liquid already gives us a lot of feasibility. So let me just go back to some of the storage options that we got in the field of energy. So here, this one shows all the different methods to then store hydrogen. And this is research that's still ongoing, with ammonia being at the top. So although we have all these different borons or amides or anything that we got in there, still one of the best. So that's the reason, because there's not been a lot of push on in the improvement of some of these materials. Now, what people are looking at is now methods into how to carry some ammonia in a more efficient, less toxic way. That is something that is important. Not the ammonia storage itself as a liquid, because again it's already been highly efficient, but it's how to move it in a safe way. And with that, all these materials, or many of these materials, are playing an interesting part. So research going on in the material science and catalysis, they are looking into honeycombs, into porous materials. Magnesium seems to be a really nice player into these talks where people are looking into combinations between boron and lithium to then produce pedals or pedals and designs that will maximize that. So if there's a sudden release, the ammonia won't be leaking out where it stay there inside of the material. They can get it out using some thermal applications. So that's where the research is at the moment. There's a lot of going on. And again, if it's managed to then be out in an efficient, cost-effective way, it could be the way to then deliver the hydrogen. Because again, the toxicity and the nuisance won't be an issue.
Thanks. Because I know a lot of people talking, there was a Celtic published last year talking about just store hydrogen in salt cabin, which is very cheap and cost-effective way. So I'm just thinking if we use it, how competitive it can be.
Yeah, well, in the case, for example, comparing it with the caves, you have the distribution of ammonia wherever you want, whereas in the caves, you will have to then be located just in that particular location. And this goes back to, for example, our UK system. We have the T-site location that we know we're going to use for caves, whereas we don't have that opportunity. So it's one of, just like that, could be an opportunity for the decentralization of that hydrogen storage. That's what ammonia offers. And again, history of 150 years with 200 billion euros being moved around that we know how to handle. So for example, ports, gas turbine and power systems, furnaces, large scale, all of those, they have some ammonia facility for denoxing purposes. So people in those facilities, technically, they know how to use it. But again, the hydrogen is something that still they don't. Now, being said that, and as I said, we have that ammonia is going to play its role in some niche applications. So it's not going to be the final product. It will be a combination, as again with all the other vectors, but it will definitely be part of it, especially for those decentralized, long distance, heavy duty type of systems. I think it's where we have the ammonia possibility.
Thank you very much.
Hi, Professor. It's a very interesting presentation. Thank you. And I have a question about the environmental impact of the ammonia, and the impact you showed us is the in-use stage or the whole life cycle. What's the environmental impact of the upstream of the ammonia? Like how many waters we need, the water source we need to use, and what's the environmental impact of the nitrogen production? And if we calculate all this together, whether the ammonia is still a green or zero carbon fuels in the future.
Yeah, no, it's a very good question. And again, on the environmental impact, there are many things we still don't know. So, for example, in the case of the end user, as I mentioned, we'll have loads of nitrogen, loads of water that will be produced. So how is that going to impact the surrounding environment? We still don't know, because we're talking about having ammonia that is being produced again in Chile, that is going to be born in the US or consumed in the US, that will be then fuming all this water, nitrogen, that we don't know what impact it's going to have on the nitrogen cycle. Now that is something that we need to study. When it comes to the cases of where are we going to get all that water, how are we going to get all those resources, one of the interesting things, and that I was very glad to hear about just recently, was that there's a lot of developments worldwide to then start using seawater directly. So instead of using the water that is for human or animal consumption, and now companies are talking and developing systems that will start using seawater. One that is really interesting is called Dolphin. Probably just keep an eye on that. And it's UK Welsh based, I think. So they have now some developments. They announced them just recently with a big project sponsored by the UK government, where they are now developing these technologies for Japan and also China and many other sites, where they feed electrolyzers, feed osmosis processes, desalinate, and then the water use it for production of hydrogen. So that is something that now is happening. And if that is scale up, and they promise that it will be scale up again, large scales, megawatts, then that means that anywhere again can be potentially a place to produce that ammonia, instead of using resources. Another way is as well using some of these waste streams that they contain a lot of ammonia, but that's as well another thing.
I like the fact that you acknowledge that NOx is such a major greenhouse gas emitter. I'm afraid I didn't quite manage to follow all of the information. So are we now at a position where the NOx emissions are lower than the CO2 emissions would be, or is that something you're still working on?
Yeah, well, that's what we're working on. And for example, the developments that we have done, and similarly goes to some of the other developments that companies and institutions are doing at the moment, have to do with some fundamental research on the use of these interesting physics, plasmas, magnetics. For example, in our case, what we're using is stratified combustion to then bring down the NOxes. So for example, in this particular case, we were operating at 20 kilowatts and we don't have any NOxes. And now we still have some sleep ammonia. And the sleep ammonia, the idea is that we can then sequestrate it by condensing all the amount of water that we're producing. It's around 35%. So we can then bring down that in an order of magnitude. So these systems can be very clean. Now, the question is, this works at 20 kilowatts, that's great. Is it going to work at a 1 megawatt? That's what we need to find out. Similarly, for example, in the case of the furnaces, large scale gigawatts power that, for example, Japan has been developing, they are producing less NOx emissions than the coal. And the research is trying to then bring them down even further. One of the interesting things about ammonia is that it's used in power plants for denoxing. So the same ammonia can denox the NOx that is being produced by the burning of ammonia, which is what people are looking at. So that's what the research in combustion is all about now these days. Yep.
You had a graph, I think, fairly early on, which showed like the levelized cost of energy of ammonia versus hydrogen in different countries, and then a combination of both.
Yeah.
And there it is. So 2 questions. When you say both, is that using a combination of hydrogen and ammonia separately, or is it using like a blend? Blend. Okay.
It is more like a blend. So what they were studying was all these different locations in the US, and depending on where they were located, would be a hydrogen economy or hydrogen-based city or an ammonia-based city. So if it was close to the sea, it would be probably more hydrogen. If it was just closer to a port that would provide for the ammonia, it would be ammonia. But then once that they combined both, they found out that levelized cost of electricity was the lowest. And it was because instead of thinking, let's have a big hydrogen producing system to then feed all the grid, or have a big ammonia facility just storing all that energy, we'll have a smaller hydrogen system with a smaller ammonia storage facility. And that brought down capex in all the cases.
Thank you. Yeah, that answered my second question as well. So that's great.
Sorry. I'll just continue this question because I think the US electricity market is quite unique because you use location-based, which is not existing in most countries across the world. So I wonder how indicative can be, like we use that as evidence to support our decisions.
That's again one of the things that I think is a really good point and that needs to be done. So part of the research that we're trying to do is trying to find out the different levelized cost of electricities and levelized cost of hydrogen. So we know what would be the difference between scenarios. So one that we have done recently that's really interesting is on Milford Haven. So how would that be different to the LNG that they're already exporting into the grid? So ammonia would be a case, or liquid hydrogen, and on the same basis, cases like, for example, Teesside, or bringing in the Celtic Sea, yes, every different economy will have their own analysis. So depending on, for example, how they integrate their energy systems. Case of, for example, France, they could produce something called pink ammonia that is nuclear. So again, coming from nuclear reactors, it's cheaper. It's much more easy to obtain, obviously, and they have all the infrastructure to do so. So again, one of those cases, again, with France, just those boundaries will be different to, for example, a case of Germany or the UK that is wind. So yes, every economy will have their needs. But it's one of those cases that now we need to then have this kind of analysis combined with demonstrators to then give us what is the best option. Yeah.
I have a question related to the ammonia cracking, like how it is done, either by heating ammonia, and if it's by heating ammonia, then is there any chance of NOx emissions while cracking ammonia?
Yeah, that's a really nice question, and we're already doing it now. And it's really fun because you have, for example, the way that we're doing it is via thermal cracking. You have 2 other methods, that is with catalysis, and the third one, plasmas. That is something, again, that sometimes is non-thermal. So the cases, for example, that we're exploring is having the system that is containing the ammonia to then reach temperatures high enough to then start splitting up the molecule, and we're producing nitrogen and hydrogen. So right now we have managed to produce up to 70% cracking, meaning that we produce 70 of that whole ammonia in converting into hydrogen, nitrogen, and the only thing that remains is just the ammonia that you didn't crack. Because you don't oxygenate, you don't put any oxygen for the combustion in that process, then the only thing that you get is just those 3 molecules, which is really good. Now, what research is going on in this area is try to bring down the temperature for the cracking. So thermal cracking occurs around 650 degrees Celsius, whereas the cases for materials that are very expensive but very clever can go up to 400, 380 degrees. So that means that as long as you have, say, some waste energy stream that can provide, say, for 450 degrees, like in a gas turbine, you would be able, with those materials, to then crack the ammonia, produce the hydrogen, and then use it in the process. Or receive it in the port, have a system like an electrification system or electric furnace to then pass it, and then that way as well produce the hydrogen. Now, the main problem with that is that the amount of material that is required is, again, massive. And again, the cost of these clever materials, ruthenium, barium, lithium, cesium, etc., expensive, really expensive. So that brings these cracking systems to a very not cost-effective solutions. They become, again, just out of the norm. And that's one of the reasons, because now people are looking into a combination of both, where you have some of these clever materials combined with the thermal cracking. But that's what now are people looking at. So in the case of, again, large scale, the port of Singapore, the port in Belgium, one in Germany. Here, Liverpool, for example, is now considering using it. In Canada, and also one in Japan, are considering having crackers large scale to then distribute hydrogen into the grid, receiving ammonia at port and then distributing it that way. But yes, NOxes are not produced. Yeah.
You mentioned quite a lot of challenges, I suppose, and I think there was a slide as well that had a list of them. It might be a difficult question, but what is the biggest challenge that you're seeing? Is it the public perception, the NOx emissions, or kind of the requirement for more demonstration projects to prove that ammonia can be done, and hopefully eventually costs come down as well?
Yeah. I guess depends on where you are standing. So if you are standing, for example, I guess in a directive board in a company, it will come down to then the costs. They're just bringing down the cost of ammonia, and then how we're going to then sustain this, because again, that's one of the main issues, 3 times more expensive than the one that we usually get using CO2, right? But we're obviously, because of inefficiency, producing more CO2 that way. If you were in a community, part of the public will be obviously toxicity. Like how toxic can be, and that again has been one of the major issues that we face, and especially people that are well educated. When it comes to that, they realize that there's a potential of being killed by a release of ammonia. So it's like immediately freaks them out. I mean, it's something that is already going on with the case of hydrogen, isn't it? That people are still concerned of blowing up because they have a leak. So in terms of again, a power operator, it would be the case of maintaining stable low NOxes, and then finally, again, on the economic side as well, will be the production. But particularly, I believe that putting everything in context will be the public perception at a government, local, national level, that still is reluctant to see that as a vector that could help hydrogen to happen. I think that's the main issue, because they don't understand. They initially think, oh, this is going to kill us. Like, is it? We have been using it again for that long and it's not killing us. But you're going to use it differently. Yes, I know, but that's the reason, because we're doing all this. So yeah, I think that's a very good question. I will come to them. Yes.
Thank you for a very informative and data-rich presentation. My question is about the outputs of all this research in terms of infrastructure, and how you see ammonia plays in the hydrogen renewable energy economy in the future, particularly as far as that applies to the UK.
Yes.
And you mentioned some forms of transport, which are like heavy shipping, rail and so on. Does that imply that you're going to look at sort of storage around ports and so on?
Yes, totally. Yes, the way that we've seen it is, this is an idea that we got right now, and that is being expanded nicely, and we got some infographics now that we're just about to release, to have that hydrogen production sites that potentially can use the ammonia storage concept. So once that we got that, then it's going to be distributed to 2 different locations. One, again, will be obviously through all the shipping and cargo, the city gate terminals, and that could be a port, could be outside of a city, could be in the surroundings of skirts of a large farming community, etc. And then with that, it will be directed either as an ammonia directly, that can be used for fueling and fertilizing purposes, the way that, for example, the US is doing already. So they have a long pipeline that is crossing the country and then finally reaching these petrol stations where they fill in the ammonia. Are we going to do it in the same way? Probably not, because of our regulations. Probably could be something that is automated. So again, now the farmers are doing it directly. It could be something that is just done by automation. In the case of the cities, I don't see the ammonia going in, again, because of this reluctance of people saying it's no way forward. It will be something that will require cracking to then deliver the hydrogen into the natural gas grid, starting with the 20% that we know we can reach, and eventually start dephasing with the increase of hydrogen seal prepared pipelines. So the ammonia will be a supporter to that hydrogen. We need some additional hydrogen for the gas grid because we are running out. Then we have the ammonia storage that can be put into the system, or again for communities just replacing the LPG that they're using at the moment. So then do it that way.
So would you say it's analogous to LNG today then?
It would be analogous to LNG. Yeah.
That's what I thought.
Yeah. So the studies that we have done in technoeconomics, again going back to the Milford Haven case, it's based on the LNG case.
You mentioned before that there is no regulation yet, but I kind of don't understand. In South Korea and Japan, they are making the ship is going to be launched the next month, you said. There's a plan with the W2, and the many parties start making the ammonia statement. And no regulation, and they already apply in the life.
I know, right? It's crazy. It's one of those things that are just crazy. So the way that it goes is that right now they are capable in all these ports and locations to receive the ammonia, because again, it's just coming as another chemical in the way that has been transported over years. Now, the regulation that doesn't exist, or the regulations that don't exist, are those for the use of ammonia as a fuel. So those are the ones that don't exist. So all these systems that now are going to be released next year, this power station and all that, they are on their research development agendas that are still not to the commercial purpose that again is needed to then get them to the regulation level. So the IMO, the Maritime Organization, they take years just to then get a regulation. I think the latest is still tracking down the methanol to then be released. The case of ammonia is just again behind that. So until methanol happens, ammonia will happen. But the companies will already have the system. So they are ahead of any regulation. They're just cleaning up the gases, just as long as nobody dies, just prove it and then go ahead. With the cases of for example, the power stations, it's just the same scenario. And when they're replicating and doing this type of tests and commissioning, they are now pushing for a standard. So the one that we've been involved in is a technical specification that is the precedent of an international SIO standard. And the reason is that this company, the one that I show you selling these burners, contacts people in Europe, the US, Asia, and Africa to then join this board. So we could agree on a standard. And what is all for is just to agree this goes ahead. We have a meeting next week, and with that, we have a specification that can be applied now for anyone that is buying our burners. So it's a commercial game, which is very interesting. But yes, the first probably standard that we'll see is the one that is operating on the furnaces because of the speed that they take to then put them together. Yeah.
Well, I'd like to thank our... Oh, sorry,
One last question on the third generation technology. You mentioned something about fuel cells and way generally in the direction of the third generation technology early on. Are you saying that you're looking at proton exchange technologies but not electrolysis?
Yes, exactly. It's proton exchange. So yes, the way that I understand it, because yes, I understand the composite much better, well, to some extent, is that you have the proton, yes, from the water molecule, the H plus, being again moved through the membranes. So once that it reaches the nitrogen that has been captured, and they use lithium recombinations, the lithium is the one that captures the nitrogen with the molecule of the hydrogen, and then they just get together to produce the ammonia, releasing again back into the membrane the lithium to then restart the cycle.
So what are your feedstocks for
Water and air.
that?
Yeah. There's a company in Australia that has been working on that. I didn't add it to this one. I should have. But again, this is the one that has been now showing efficiencies around 46% with really nice results. Company is called Jupiter Ionics. And again, they have a nice venture supported by the University of Monash. Really nice stuff. And similarly, the US and some in Europe are trying to then go in the same area, trying lithium as the basis of the process. There's another one that I didn't mention, that was the use of thorium reactors. That's a really interesting as well, mind-blowing type of concept. So there are companies across now all different continents that are trying to then create these small reactors the size of this void that we have between tables to then produce very large power outputs in the range of 100 megawatts. And the reactor works on molten salts. So it seems to be, according to them, very safe in the production of energy. But one of the main reasons, because they want to do it that way, is that it can be put into a container, and that they just replicate it and then copy 10, 20 times to produce 100, from 100 to a gigawatt power. But they're interested in both the production of power directly into the grid and the production of the ammonia. Because again, the temperatures that they reach can produce the pink ammonia as a residue and then feed into what is these markets. So they promise, as part of these developments, that the ammonia produced that way will be half the cost that we got it right now from the generation one. That's what they say. At least that's in all the documents. So if that happens again, could be that we end up with thorium reactors. Apparently thorium is more abundant, much more abundant than uranium, and that way will be much cheaper. Again, small systems, all confined, easy to handle, to then produce all this ammonia half the costs. That's again on the promise. Oh yes, lots of interesting things around production. Yeah.
Last question.
Yeah.
Does ammonia have the potential to completely replace hydrogen as a storage potential for the intermittency of renewables?
There's this, we published recently a Royal Society policy briefing. It's called Large Energy Storage. And this is just 5 months ago. And the whole rationale is looking into all the different aspects of what could be the different methods of storing energy. There's one paragraph, and if you put in the search tool, ammonia, you will find it in that document probably 20 times. So the whole thing is that in one of the paragraphs, there says, well, ammonia is still not a vector that again will make a different or massive contribution commercially under the stage that is at the moment. However, if some of these technologies becomes viable, if this half-cost thorium reactor becomes a reality, then that will change entirely as a breakthrough of technologies on how we're going to store energy from the future. And this goes back to, again, thinking about potentially fusion reactors. So if fusion reactors become a reality, you will have the potential of then distributing ammonia, ships, carriages, lorries, etc., from those reactors into these type of systems. And then again, ammonia will make a whole difference. And again, anyone in the world will be able to produce their own ammonia for fertilizing or storage purposes. You can end up having your own ammonia production unit at home with a solar panel, store as much energy as you want, and then feed the rest solar. And when you need that energy in the winter, you can then burn it and use it efficiently. So everything will have to do with the storage, if it's safe, if we have the right regulations, and again, the cost of this being affordable.
I think it's been a wonderful presentation, Augustin, and you've obviously sparked a lot of interest with some really challenging questions, and you've risen to those challenges and come up with some really good answers, so thank you very much. And a little thank you for your time.
Oh, thank you very much, yes. Yeah. I would say
Carbon neutral wine. Hope it tastes good. Carbon neutral, that's the most important bit.
I was going to propose it and then drink it now, but I don't think that we have enough.
We've got some plastic tumblers.
Yes, anyone for it? Just a little bit. No, yes,
We'll let you enjoy it. You probably want to chill it.
Thank you very much.
Yes, thank you so much for coming. I'd like to thank all of the audience. It's been lovely to have such a well-received presentation and some really thought-provoking questions. I hope you'll join us again at our AGM where we'll have another presentation on the 12th of June and we'll be back in this building. You can contact myself or Emily, or you can just look us up on the Energy Institute Southwest and South Wales branch. You'll also find our Young Persons Network, and we've got two representatives from our Young Persons Network here today, John and Kaiwan. So if you don't want to associate with us old fogies, you can associate with Young Persons Network. Thank you all for joining us today. Feel free to take some refreshments on your way out. It saves me carrying it up the stairs. Thank you.